So yeah, for people who are not familiar with compute shader, like when you deal with pipeline, you always have this processing of vertex which goes to pixel, except this case of stream-out. So you always have this pipeline of vertex tessellation, which is optional. Then it goes to geometry shader and pixel shader. But they always all these elements are kind of connected together. Like you need to pass through vertex shader to go to tessellation or to go to geometry shader. It's like a flow. Compute is completely different because compute is just a unit on its own. So it's just, you don't run compute with something else. You just run compute shader. And it's really designed to do, actually it's really designed to do nothing really. It's like, actually, if we want to consider compute, it's just a number generator in the whole concept. So the idea is you say, I want to, like when you have this null geometry, for example, you want to say, I want to draw n vertices. So compute is exactly like that. You want to say, I want to run 64 elements of something. And then you do the reading and the writing. You have to do everything yourself. So like when you had, for people who were here yesterday, like tessellation, for example, is building this UV for you, but compute does nothing. So when you do compute, you're on your own. That's the idea of compute shader. So, well, the fact of you being on your own gives you, well, complete flexibility because you can do a bit whatever you want, but obviously there are some rules which goes with it and it makes it quite more difficult. So I'll go through the first patch, which is really an overview on dispatching. So instead of, when you run compute, you don't run geometry, you run just number. Like I always try to consider like compute is just an I spread in some way. It's just like you say, I want to go from number 1 to 64. And when you do a 2D dispatch version, if you want to run compute for more 2Ds, then you have across 2D or across 3D. So it's basically, it's really a I spread with across 2D or across 3D. It sends indices. So you say, I want to run like 1 million elements, and you receive the index. So it's really just it's an I spread with cross generator, and then you receive where to. Ooh la la.
Fire alarm?
I don't know.
The apocalypse stuff?
Yes, probably.
Third, right?
Yes. So if we look at, if we look at compute shader, actually that's, here. Yeah, if we look at compute shader, the whole thing is actually much more like let's call it minimalistic. So the initial compute part is just, you don't have vertex ID or anything on inputs, you have this dispatch thread ID, which will just be this, like, it's like if you build in C#, you build a for loop, and then you say process this element at this location. So the for loop, at some point you have this I iterator value, and then you do something with this I. So with compute, actually this I is generated somewhere else, and depending on the group, you build the I generator yourself. So if you do a 1D version, everything is quite straightforward. You have here, so it's a 3D dimension. So you have this cross, it's like this cross 2D and this cross 3D version. So you consider that's my I in x-axis, that's my I in y-axis, and that's my I in z-axis. So that means, but this is compute works with groups, so I will go a bit later on that.
How many threads you can apply maximum?
That will be exactly in that section here. So the only idea with when you do a for loop, generally everything runs serially, whereas with compute everything runs in parallel. So you have tons of units which are gonna try to it's gonna try to process everything as fast as possible. So, but every unit is independent of each other. So the idea is also you have the concept of group. So you never say I want to run one. Like if you want to run, like for example, 64 element, you don't say I run. You can say it in that version. So, and you'll have your dispatch of I run 64 elements like this. So you have your, when you dispatch, you say I want to dispatch 64 groups of 1. But generally what for compute is good at is especially to run plenty of those groups in parallel. So you want to say, I want a group of 64, for example, and that means every unit will be 64 elements. So it's like you say one unit will be I spread between 0 and 64. The next unit will be the next I spread between 64 and 128. So every unit, you always send blocks. So you don't send one unit at a time because the idea is to have everything parallel. So to have everything parallel, you send blocks. So in 1D case, you would have a 64 version. So dispatcher does not, you have different nodes to achieve that. So dispatcher does nothing for you. So for example, if you want to say I have a buffer of 1004 elements, so that's my buffer. And you have a group of 64 here, so you have to say I need to divide by 64. So that means you need to send 16 groups, each group being 64 elements, which goes to the compute shader, which will bring you, well, 1024 elements at the end. So that's your buffer size. And dispatch thread ID is exactly this number in 3 dimensions. So for example, if you have, actually, I'll just do a version of it. So yeah, if like you have this dispatch thread ID, so let's continue. So when you have this dispatch thread ID, it will be the counter. So yeah, compute don't expect any data input like vertex shader pipeline, which will say, I want to take this position as input, and I give you texture coordinates. Compute has nothing as input. You always have to read manually, and you have to write manually. So if we check like that, it's just an I spread in compute, so you just output the number. So in that case, TID will always be which is the absolute number. So in a for loop, if you consider the for loop analogy, it will be this I version. So one thing which is important, because you think in groups, one thing which is important, you have the cases where, for example, here I have 1024 elements, and I have a group of 64, and it's perfectly divisible. So that means like I can run exactly 16 group, and 16 group will exactly fit the 1024, but it's not always the case. Sometimes if I say something like I have Actually, if I have 65 elements to process, and I have a group of 64, I still need 2 groups, because obviously, like if I run only one group, I will run 64 elements, so the last one will not be processed. So you always still need to run a little more. So that means in the case of 65, you need to you need to run 2 groups. So you will run 128 dispatch, but you will have a few which will do nothing. If we consider it on 64, it looks like a big deal, but in the case, if you start to think into like 500,000 elements, like processing 63 elements on top is just not a big deal anymore, because you can really run it in parallel instead. So in that case, like dispatcher doesn't do it for you. So that means you have to say number of group. So you have to think of to say, okay, 65, you can do different ways. There's always different ways to do it. So you can say mod 64, and you have divide value. So that's that's the group size. So that's 1.01. So you can do you have a frac, and yeah, actually we should have this ceiling operator, but it's not here. And plus. So if we perfectly equal, we can just divide by 64, but if we're not perfectly equal, we kind of need to always add one group, basically, to make sure we need to process at least the amount of elements. That's the idea.
So the slowest group is the limiter?
Sorry?
If you have a group that's 1 element, one group that's 64 elements, and the second group is like blocked until the bigger group finishes, right?
It's a bit, it really, well, it's not completely waiting, like it will try to send it can send several groups at the same time, but it depends on the workload of your compute shader. So if your compute shader has a heavy workload, it will maybe not be able to send a new one, but if your compute shader has a light workload, it might be able to send several groups at the same time, but there's no, well, I can give you a link because for that which describes it, because that's very, yeah. It also depends on the graphics card model driver. So generally the graphics card plus driver will try to balance the workload of the compute shader. But there's no rule of thumb of if it will run one group at the same time or several. So now, yeah, here we have this dispatcher, and if we work in 2 dimensions, which I will show after in some examples. So yeah, here we always have to do this calculation, so that's why there's this utility node now, which is called dispatcher X, which will say you set your thread group to whatever is matching in that value, and you say the number of groups of elements to process. So this one you don't think in group anymore, you can think in elements. So if you say I have a buffer of 65 and a thread group of 64, so this dispatcher X works. It does this calculation for you actually, because well, you have to do it all the time. It's gets boring after a while. So this one is designed to do it exactly for you. And there's a version which is dispatcher XY, which will do the 2D version. So you have the size in X axis and the size in Y axis. So if we do a 2D version, actually, I can. yeah, in the case of 2D version, obviously it will, so instead of sending numbers between 0 and 24, it will render an array. So it will be exactly matching this value. So if we say I want to say from 1 to 0 to 8, it will run here. I'll just put it as. So it will do the pair 0, 0, 0, 1, 0, 2, 0, 3. So it's like a 2D. It's really like it will build a grid index. It will build a grid of index. So in case of 2D, if you dispatch in 2D, you can easily access pixel location because suddenly you say I want to access row number 0 and column number 5. So instead of having to find where is the exact pixel by hand, you have row column access because textures work as row column access. So when you dispatch, you have these versions of dispatcher, so where you do it by hand, basically. So you know in CPU what to send, how many elements to send to the graphics card, and you have those versions which are called indirect dispatchers. So the idea is sometimes, for example, the number of elements is somewhere on the graphics card. So you don't know the number of elements to process in CPU. So you can't really use those nodes because you can't really put that number here. So in that case, you have this indirect dispatcher, that means you have a small GPU buffer. So it's like a small structured buffer, which contains. Actually, when you send, if you consider it as a struct, so you have int x, int y, so it's like a vector3 integer version. So a dispatch argument, you have a small buffer in the graphics card that contains that value. So instead of providing it on the CPU side, this is provided inside a buffer instead. And you have. Well, one thing with dispatch is you have some limitations. So for example, like if you do a 111 if you do a 111 num thread, you're not allowed to send more than 65 536 groups. It will work on some cards, not on other as usual. But generally it will start, if it works on some card, it will get much slower. So that means if you process a num thread of 111, the maximum number of elements you can process is 65 536. So that means when you're setting up your group size, there's also the aspect of how many elements you will process as maximum. So if you have a group size of 64, for example, you limit it to 4.1 million elements, which sounds a lot, but in some cases very little. So we used to use 64 groups for quite a while, but nowadays, 128 brings you to 8 million elements. So here you have a little table that will tell you, depending on the group size, that will be how many elements you can expect to process. If you can't, sometimes if you can't process, if you have a group of 64 on more than 4 million elements, you can still do two dispatch. So you can do one dispatch which does half of the buffer, and another dispatch which does another half. So you don't need to read and write everything in the same call. You can still split the load in different calls as well. But in one call, that is the limitation you'll have.
Sorry, but can you explain? I mean, I know we talked about it privately, but I'm sure some people would like to hear when we can go up to 128 rather than 64. So you were saying this depends on the generation of the graphics card, how recent it is?
No, it's, you can put 128 anytime. You can go up to, you can go up to 1024 on every card, pretty much. Like any card that supports shader 5 should have this specification that they should support this exactly. But some cards will perform better in some case, some cards will perform less. And also, depending on your shader. It really depends on your workload. So like managing group size is just a job on its own somehow sometimes. It's like something you have to try and experiment on. At some point, that's what you call sweet spot. And you find the right number that fits the right workload and you stick to it. But you generally tend to, 64 tends to be too low nowadays a bit. But between 128 and 1000, you have to try all of them. And you have to compare the speed difference, and at some point one might be faster or not. It depends on what you do in compute, of course. But you can go from 1 to 1024 on any card. It's not dependent on it. But the group might affect the speed of execution. So the limitation is, as I was speaking about 1024, when you have your group size here, you are limited to 1024. So you're not allowed, if I put 2048 here, you can see, well, it will say the product, well, actually the shader will not compile, so at least you will have a meaningful error directly, which is useful. So it will say, no, sorry, we can't do groups of more than 1024. And it's the product of the argument, so you always have to think in several dimensions. So here it's a 1D version. I'm at 2048. If I go at 1024, then it compiles again. But yeah, it's also as a product. So here both are lower, but if I do that one, 512 and 3, that will not work because it's 512 multiplied by 3. Like you always multiply those numbers here. So that means when you process, if you need to process more than 67 million elements, you will need to split the work across different dispatch. Or you can do dispatch which process 2 elements at the same time. That's one thing which is possible with compute. And the last thing, there's obviously one exception to confirm the rule, is the z-axis is limited to 64. So you're not allowed to have a z dispatch of more than 64. So yeah, so as I explained, one thing with compute is one thing when you process, which is really different from pipeline, is when you do pipeline, like when you arrive in the pixel shader, you are processing that pixel. So you already have a dedicated pixel which is assigned. So you return a color value, and this color is that pixel. In the pipeline, you can't really say in the pixel shader, oh, I want to write to that specific pixel. The pixel is already assigned to you. Actually, you quite can do it in pixel shader, but that's a bit hacky. But in the standard version, when you reach your pixel shader, you're processing a pixel. In compute, you just have a number. So that means you can read anywhere and you can write anywhere. So So I'll just do a 1-1. It's not really recommended, but it's to explain the version. So I will just process dispatcher. I'll just process 4 elements to see a bit how it works. So you have your dispatcher, you have your compute size, you have a RW buffer, which will say you want to write somewhere. But you have a renderer buffer. which has 4 elements, and stride is size in bytes. So when you render to a structured buffer, you have this, it's the size of the struct, basically. So in that case, we're doing integer, so it's 4 bytes. And we do a read back buffer int. And for the moment, it's returning 0 because I'm not doing anything in there. So now if I say output buffer tid.x equals tid.x. Now it's just a counter, so you can see here I'm just writing in the, it's like really you think you process an array. Really, it's not, in many cases you have of compute shader, you can just have it reduced as you're just processing an array of data, and each elements can be processed individually, it's very easy to put in compute shader, and it's very easy to make it in parallel because no calculation depends on each other. So in those type of cases where it's just a counter, everything is really easy because you don't need the calculation of slice number 2 to calculate slice number 3. But here I'm processing one element at a time, but what I totally allowed to do is I say I want to send only one group, and I want to write to index 0 equals 10 because I want to. And I want to say in the same part, I want to say buffer number 2 equals 35, for example. And then we have 35 here and 10. So you can read where you want, you can write where you want. That's one of the big differences with compute shader. You're not limited to like, oh, process that vertex or process that pixel. You can say, you can read anything and write anything in any order you want. But the standard still use pattern will always be something like, well, and dispatcher X. So that will, generally, if you want to process as arrays, that will be the standard pattern. And for example, you have a so yeah, here if you can of course read and write anytime. So if you think of you can really think of compute as a you can really redo most spread operators like you have in 4v. Most of them you can quite easily redo them in compute shader. Like if you think of add add operator, and if you think slice-wise, you always have to do mod operator like this. So it's if you want to think in spread, you do spread is exactly working that way. So if you try to read over the size of the array, it kind of cycles through. And let's read back float. And So yeah, that's basically, if you consider that's a standard operator. So if you want to think spread, like you have to just add this input-output, but any node you have in 4V, you can which process data. If you really need to add extra performance, all of them, you can do them directly in compute on the whole, because every element is slice-wise, everything is very easy. Like you don't have to think about neighbors much, so anything that can be done slice-wise, instead of using the spread operator, you can do the same version with buffer on compute, which will give you pretty big difference performance. One thing which is important, if you don't process slice-wise, like here you process slice-wise, so you don't have this problem, because that means, for example, if this buffer is only size of 2, yeah, you can see the addition is going, it's the same as the add operator in 4V, because we're cycling through. But in the case you're not cycling through, like also it's guaranteed by the driver, because it's the DX specification. So the driver should do that. If not, it's a driver bug. If you try to read outside of the bounds, like it will return you a 0. So if you try to, here my buffer is number 4, is only 4 elements. So if I want to say no, I want to read element number at index 8, it will return 0. So it will not crash, it will not give errors. The specification says if you're outside the bounds, I will return 0. So you have to take that into account in your calculation. So if you might read out of bounds, you have to take care of that. And if you try to write outside, so it will automatically do nothing. So it will also not crash, it will not write somewhere randomly. It will automatically see it's outside of the area of your buffer, and it will automatically do nothing. But the fact of reading 0 by default can be quite a problem. So you have to be you have to take it into account, because if you multiply by 0, you can have, obviously it will be 0, for example. So it can create quite some problems. So what you have to normally also do, I'll just get rid of this one for now. So if we go back to this standard pattern, I'll go plus effect here, add, yeah, okay, add with check. And here. So in case we process slice-wise, we don't really have the out-of-bound issue. But if we just want to say, no, I just want to pass the value and multiply by 2, for example. What we've seen is we process group. So in that case, I process group of 128. But you can actually see my buffer is only 4 elements. So that means I do a lot of those writes which are completely wrong, and I do a lot of those reads which are completely wrong. So normally the standard pattern is to always yeah, you will, the standard pattern is normally every time you run a compute shader, that should quite be the first line, which is an entry of pretty much 90% of them. If your ID is outside of the boundaries, you should just exit as fast as possible. You should not try to process anything and finally read 0 and write nothing, because you're using those processors for doing work that will be cancelled at the end. So the standard pattern is to add this condition. You say, okay, I'm out of bounds. just go away as fast as possible. That's never costing anything to add it on all the thread, and actually it can also make things faster because generally that gets grabbed by the driver also. So you also have like, yeah, that's one of the things with compute also, like pixel is not assigned to you, so that means nothing is done for you anymore. You have to really take care of things a bit more in detail. So you have to take care about where you're reading, you have to take care of where you're writing, but you have to take care you're reading in the right places, and you have to take care you're not writing in the wrong places also. So you have this full freedom, but you have to do everything. Nothing is done for you. So all of this needs to be added by default.
Would that also help optimizing if you got 65 element on a 64 group size? Because it kind of ignores the other.
Well,
if you have 65, then obviously we need two groups.
You need two groups, but as soon as you early return, one of the things is as soon as you early return, you have this thing that these units are available again. So that means this, like, as long as you use processing this data, like if you don't have this early return, you're using this unit. So you use this thread. It's like if you have 8 processor on, if you think in CPU, you have 8 processor. If you're using the one processor even to do nothing, you're using this processor. So this processor is not available to do something else. So the early return helps because you suddenly say, hey, I don't need to do anything. So this processor can be automatically reassigned to do something else. As long as you occupy it, it's considered as busy. So as long as you do something, it's busy. The early return helps to say, oh, by the way, it's not busy anymore. So that means the driver will be able to prepare another group. So that will also help performance. Oh, yes, it's boiling.
So the concept of CRUD divergence, like in CUDA, or there?
Yeah, well, compute, CUDA, OpenCL, they all share the same concept because it's all, graphics card all works the same way. Like compute is probably implemented somehow on CUDA actually inside the driver. It would not surprise too much, but they all, the card works the same, so you have just different form of implementation. Well, obviously if you use CUDA, you have a bit more vendor specific optimization. Which are, yeah, you can use byte type, for example, in compute, I think, in CUDA. Yeah, you can use byte, yeah, compute doesn't understand byte, for example, so you have a few limitations to make it more generic, but otherwise, in essence, it's quite the same. But yeah, because compute is designed by NVIDIA, sorry, not compute, CUDA is designed by NVIDIA, and it runs only on NVIDIA cards. Then they can do specific optimization for their own card, and they add specific feature for their own cards. So you will always be able to do more with CUDA if you're on NVIDIA. But then suddenly if you need something else than NVIDIA, you can't do anything. So compute has more limitations. It makes it more generic, but at least it's supposed to run on the major card. Well, OpenCL should too, but. Yeah, the big difference with compute and CUDA is they have their own, like compute is part of the DirectX scheduler, whereas CUDA is not. So if you start to run CUDA on DirectX, you need to synchronize everything, whereas in compute, everything is synchronized with the pipeline. So if you do a compute shader, when you run your buffer as output, input in Vertex shader later, like the pipeline already takes care of that, because it's part of the same thing. If you do a process one buffer in CUDA and then you want to use it in DX11, you need to make sure everything has been processed before to be able to use it. So you need to add the synchronization on top by hand. And it's really not funny. So yeah, advantage of compute is this is quite taken care of. You're running in the same scheduling as the pipeline. So everything is a bit more streamlined. So if we think still of the bit buffer as thread, one thing we can do is with those buffer is you can read everywhere and write everywhere, which is quite well useful. So for example, that's an example of doing a reverse spread node in compute. But there's two versions of it to explain how it works. So it's just standard reverse. There's nothing extremely fancy. You just reverse the array. So this one has a group of 64 here. And you have, well, the usual thing. You have your integer buffer as input. You want to do a reverse of integers. So you have your input, if you think spread thing, you have your input spread of int, and you have your output spread of int, and you want an output spread of int. But one thing is you can do it in two versions, because you can decide, like here you have this number between 0 and 65. So you can, reversing spread, if you do it in two different buffers, so that means number if you do it in a loop, it's something like that. Int y equals 0, I in lower than count, I plus plus. And out dot count minus I minus 1 equals input I. So that's more or less that what the reverse does in a loop. So the thing you can also decide to, because you can read and write at the same time, you can also do it like that. You could say output I equals so you can decide if you want to prefer to read sequentially and write randomly, or you can decide if you want to read randomly and write sequentially. So like this version, it's like versions called Gasser. It will say, I'm reading in reverse and I'm writing in order. And this one will be, I'm reading in order and I'm writing in reverse. So I'm writing in reverse order and I'm reading in the order of processing, but it's parallel, so kinda in the order of processing. So you can completely decide. You can read anywhere you want. You can write wherever you want. So you have plenty of ways to do different implementations of things. But the order where you read and write is eventually important for performance, because you will, doing it in one version or other can be really different in speed. But that's something you need to always profile. I can't really give general rules saying this is faster in this case or not. You just need to try both versions and try for yourself and use, and you should probably, standard thing you need to use pretty much every time you use compute. For testing, you should have this node attached to be able to test performance. So you should always use timestamp. You try 4 or 5 versions, and then one will be faster than others. And then you, obviously use the fastest one. So you can do it with buffer, but once, yes?
Is there like a practical limit to how many reads or writes you can do in a single thread?
You're not limited by read write. You're limited by registers. Like you have. On the card, you have this. You have memory, and at some point you have registers which are storing data to process operation. And obviously, code is counted in register too. So I think you have a limit in register. I really don't remember it. It's quite really hard to have shaders that go past that limit. I have one somewhere. I can find it back. But generally what it will do, at some point, if you start to bypass this number of registers, first the compiler will tell you. So it will say, oh, by the way, you really passed the maximum limit. And in that case, it will not prevent you to do it, but it will really be slower. So you can really expect it to be 10 times, 100 times slower when you start to have this warning thing.
And do you have to take care if you are doing multiple
if you need to write to the same place, you need to take care of that, of course. Nothing, because you're doing it in parallel. So that means in one frame, you might have like, if you're writing in the same place, if in one frame, I think the compiler prevents that to you still. Yeah, the compiler should still, if it can detect it, it's not always possible to find that you will write at the same place. But like if you have a group of here, oh, it's not doing it anymore. Ah, there we go. Yeah, so it's not always detecting it, but sometimes it does. It will say race condition, you're writing to the same place.
Because every thread is just writing the buffers.
Yeah, here you're writing same value, so the impact is not, it's not a problem somehow. Yeah. But still it will try to write to the same location, so that will eventually hurt, of course. And if you do tid.x, yeah, in that case, actually, it's actually it does you. If it really can detect it, it really brings you an error. Yeah. Like in the case you're writing the same value, it's not a problem because anyway you will write 0. So if you write 0 1,000 times, it's a bit your problem. It's gonna be slower, but it's okay because the value will still be correct. But here the value will not. So the compiler even prevents that for you. But of course, if you have something like, I think it might even be smart enough to still to detect it in that case. Yes, actually, even if you put it here, the compiler will still detect that it's a constant value outside. So it's still quite reasonably smart enough to say, okay, here I can still see. Yeah, even if you do multiply by 2, it will still. So anytime it can figure it out itself, it will give you an error. So I think you can still go to trick it somehow. Like, if you really want to do it, and actually to show the example, actually right now I really want to do it. So you, like, yeah, you have to do something like that if I greater than 0. I think that one should be enough to be finally able to do something you're not allowed to do. Ah, no, it's still not happy with it. That's quite annoying. Yeah, well, it's really smart. A bit too much to my test for. So yeah, but if it can't detect it and it happens, it means in one frame you might have one value and in one frame you might have a different value because things might process in different order. So it's up to you to take care of it. But normally because it's not desired behavior, the compiler tries to help you when it can. So one of the things we can do, I'll go through this one. Well, the thing with compute, you not only limited to buffer, you can write to any resource. So you can write to 3D texture, you can write to 2D texture. You can read to everything and you can write to everything. So that's one of the nice advantage of it. So here, that's one example which, well, if you want to work with things like LED, it's a quite convenient like module. So like with LED, we always tend to think in pixel because one LED is 1 pixel. So you can do viewport pixel routing, but you can do versions in, like if you do viewport, I think it's 16 viewports can be set at the same time. So if you want to have more than 16 layouts to write, then you can't use viewport anymore. So you can do it quite conveniently in compute. So that's one of this example. So that one is just renderer, actually texture spread. so that means every slice renders a texture. So you can, that's node, I don't remember if it's from last release or not. I think it's from even previous one. So instead of texture array, it's really texture spread. So that means you can even change resolution of each slice texture. So, well, this one just renders different segments with different resolution in and every segment is in one spread only. So, and then we want to say now we have our 4 texture input and we want to layout them in a pixel layout. So we want to say now this one, I want to, for example, I want to move it here, exactly. I want to move it at pixel 50 and at 500 is a bit too high, and at 200. So when you work with, if you work with LEDs, that's really convenient because Guy will give you a layout and it says, okay, you need to start this place here. And so you can just type the number and you're more or less ready to go. So you don't have to think about all this texture, transform and thing. You can just think it in pixel, which is much easier because people provide you pixels, so you think you don't have to care of conversion. The less work I have to do generally, the happier I am. So in that case, we're doing 2D, so we're using dispatcher XY because we're gonna write to texture. So in that case, we have a num thread here, which will be 8.8 because you want to write. You don't want to start to think of texture as a 1D buffer. You want to think of texture as a, well, 2D grid. So you want to access elements to say, I want to access row number 5 and column. You access texture by row column. You don't, if you want to access texture, you don't access texture as array buffer. You don't have to do that calculation. So actually, yeah, you can do, it's actually really simple. The whole pixel shader is really straightforward. It's not anything even difficult. So you have your num thread of 881. You go read, you can read the texture pixel. So if you do this, it's like instead of sampling, you can use this version, which is just say get this pixel at this row and this column. That's it. So it's the same as if you were doing input texture.load and int3 tid. Yeah, if you do the bracket, it's just a direct access, but it's the same operation as doing load, and load as int3 because that's the MIP level you want to access. So you just read this pixel, which gives you a color, and then you have this offset table, which will say this is the starting location where I want to push this texture starting point. And you just say, okay, no, it's just an offset at the end of the day. All these pixel layouts, they are just some little offset. And then you just write it on. I just added a little background to show the square, but that's normally, you would just remove it. So yeah, num thread will just, in that case, it gives you access to pixel. If you wanted to do something like, if you want to access the pixel and you're doing a 1D version, you would have to do the calculation yourself. So you'd have to, if you had the 6411, you'd have to say int x equals tid.x mod width and int y equals so you'd have to do the grid calculation yourself if you did it, if you want to do texture reading in the one and you have a 1D version, but considering you're working with texture, it makes much more sense to start to, you're already in 2D, so you might as well think in 2D. You don't want to add, this operation will actually slow down the whole process because you have to do them, whereas if you do a num thread of 8.8, it will be done for you. And you normally have to, obviously, what was valid for buffers is also valid for texture, so it's not done here, which is not too nice. but you have to, like, if you have to make sure you're not reading outside the texture, and you have to make sure you're not writing outside the texture. So if you read outside the texture, in that case, this doesn't use a sampler. So if you read out of the bounds, it will be 0, so it will be black, and it will not write in that case. In that case, the compute shader is so simple, you kinda can get away with not adding the. Well, in that case, I kinda know I will never do out of bounds, but you should still add it, so it should still be like int in w in h, and if it's tid.x. So yeah, in that case, well, no, I did not provide the size of the texture, so actually it's working. And size is what? Yeah. Output. 400. Yeah, so you need to do it for each dimension. In case of texture, obviously you're syncing in 2D, so you need to check if you're outside in the width or if you're outside in the height. And the group, instead of thinking of like unit of 64 elements, here you have to think of blocks of 8 by 8 texture. So when you work with textures, this is also really much more efficient to use blocks like this, because actually texture are not stored in a linear way in memory in the graphics card. So when you see OpenCV texture, where you have every pixel is adjacent to each other, like the layout of a texture is completely different on the card. So you should never expect that you never have linear layout on a texture on the graphics card. It's just bad, basically. So that means if you use blocks of 8, actually it will also optimize the reads and the writes, because you're closer to the texture layout. So you should try as much as possible not to always think in the number of dimensions. So one thing with the buffer as well, you have to think, well, there's always the term RW, which means read write. So that means you can, well, obviously read and write. So it's like a texture. If you don't clear the texture, by default we clear the texture, but if you don't clear the texture, on the next frame you have the content of the previous texture. So it's also valid with buffer. So you can, but in the shader you can read and write at the same time. Like in pixel shader, you can't read what's actually inside the texture. You can only write to it, whereas in the case of compute, everything is RW, so that means you can preserve states as well. So so I'll do it with, well, I'll do the first.
So you said textures don't occupy contiguous memory in the GPU?
The texture, well, they have this zigzag layout. I don't think I have this plugin working here, because I have a version where I share memory between buffer and texture, so I could show the layout, but I don't think. No, it's doing, it's like some form of zigzag version. So like if I do 8 by 8 grid, and let's do integer also. Yeah, like you will have pixel 0, pixel 1, pixel 2, pixel 3. That will be pixel 4, pixel 5, pixel 6, pixel 7, pixel 8. It's something like that, basically. So the when you upload a texture in memory, actually it will be reorganized that way, automatically. Because, well, the problem is you have cache lines. So that means if you had linear memory, you're doing sampling. So when you do sampling, you need to grab block of 2 by 2. So that means if you have linear layout, that means when you want to sample a pixel, you will have to read those 4 elements. And if you have a linear layout, you need to go to skip a whole row of elements. So it tries to keep things optimized for sampler usage. That's the reason. That's something, if you want, I can show it to you later at Node. I can find the example somewhere. Or I can rewrite it, but it will be a bit too long to do, but I can show it around if you want.
Sure.
Actually, it will be even easy to do it in 12, this one, because you can just share the memory directly. So, well, first thing, well, we'll go through something which is quite, well, another practical example to see what compute can do for you. So we always have this hit test. Well, when doing interactive thing, we always have need for some form of hit test. Like if you want to do interaction, at some point you need to know that you hit some object for any form of condition. So you have to say, I've been hitting with my Kinect hand, with my mouse, with a touch screen. There's always some form of interaction, so you always have this form of condition. So obviously we have a CPU version of hit test here. So, well, that's exactly when you move your mouse over the circle, it's just show it as hit. So we're gonna do a hit test version of this circle in compute instead. And it will show it's really straightforward. So you send your mouse position, so that's, you want to say that's the spread of transforms. So it's a spread of transform for your circle. In the case of hit test, we want the inverse transform. So we will send the inverse transform inside. And, and yeah, you can really think of hit test as processing something in a linear fashion. Like it's really like, so you have your mouse, you have element count, you have transform for all your circles. So you get the transform for your circle. You do a dot product to calculate the distance. So, well, this one has a mini optimization. So if we want to do the right version, if we want to do the basic version, we will do distance p dot y float to 0, 0, and it should be like it should, because it's a unit size. So you want to, the transform takes care of the scaling. So if you're a unit size circle, radius is 0.5. So you consider the circle is 0.5 for a unit scale. So yeah, that will say if the distance between my transform point is inside the circle, then I'm hit, otherwise I'm not. But what you can do is you can just do a dot product. So it's a dot product will be distance square, so it will save you a square root. And because now it's the square distance, you need to check if the square distance is lower than the square radius. So 0.5 by 0.5 is 0.25. So I can just hard code it also. So it's just a little quicker way to do so. So one of the big advantages is, of course, if you start to add tons of transform, like here I'm on 0.3 millisecond. If you have suddenly a lot of objects you need to hit test, like, yeah, you're on 0.304 millisecond with 900 objects with a hit test, and you're 10 times faster with compute. So just redoing like even small operations, small examples in compute, like it doesn't need to be complicated, but you can, even for simple things, especially for simple things, you can really have effective gain of performance because you're running it on the card. And since here our interaction is we want to change the color, you already have the buffer available. So the buffer, yeah. Only thing is this one returns the int to say yes or no I'm hit. So 1 means object is hit and 0 means object is not hit. And so yeah, the constant color will just have a float for which will say so we just grab the world transform again. We have the buffer with a hit. Actually, it should be int also, but well, it's interpreted properly. And then you say output color is if hit. Well, it's just if it's hit, use this color. If it's not hit, use this color. But you can process anything you want, of course. Yes?
So let's assume I want to compute or I want to use the result on the CPU. So I want to get it back down.
If you want to get back, you have this read back node.
Yeah, but so let's say I just want to have give me the index of the hit.
Ah, the index of the hit. Well, okay, that's one. Well, in that case, what we need is you need is append buffer. So the okay, so if I just put it a bit smaller again, so we can see. So in that case, if you want to get, like in that case, yeah, you return a Boolean table. But what you can also do, yeah, is you can say, I only want the index of what's hit. So I can do it directly. It test circle append. So in that case, you need, in the case we want to start to filter. So for the moment, we only sort in the way of you have input and output, so you really think of a spread operator. But sometimes, if you want to think about this type, like set of nodes, like select, exactly, like select nodes will select inside the buffer. So graphics card provides one way to do that. It's called append buffer. So we have the same dispatcher here, like you have the renderer here, and you have to say reset counter should be set to 1 in that case, because now we have an append buffer. So basically an append buffer, it's just a buffer actually. So it's the same buffer as everything, it's RW, but the only difference is somewhere there's a counter, which is stored to say, it's like a stack. You can think of an append buffer as a stack, which is push only. So you're only allowed to add elements to it. You're not allowed to remove elements to it. So you can add, you just say append. So you don't say where you're writing, you just need to say append. So if we take, let's even take advanced version. So it's the same thing. You have buffer mode. You need to say append and enabled and read back buffer int. And this goes here too, and mouse, 512 I think, and mouse goes here again, and world here. So so in that case, instead of RW buffer, we need to use append. But now the problem with append is, well, as I say, append is you only can push to a stack. So you don't know where you're pushing. You just say, add me an element. So basically, it's just a counter if you want to think about it here. So now we want to say only append what's hit. So you need to add a condition. So if hit, output buffer.append, and you want to put the index, so it's tid.x in that case. So now you can actually see on the readback it has the index. But now the readback is only if you want to do that more. Like the problem is the buffer doesn't have any concept. The buffer is still 512 and you have a counter. So if you think of append buffer, what happens when you call append is you have a counter stored somewhere, just a number of elements. This reset counter makes sure I put it back to 0. Actually, I should. I put it back to 0, and when you call append, it will say, take this counter, increment it by 1, and write this element at this, at the old location. So it's like interlocked add. If you used interlocked operations, it will be an interlocked add of number and write at the old value. That's exactly. You can rewrite append in compute if you want. It's already there, so it's quite convenient. But the thing is, it doesn't know about the. So now the counter can be 0 and 1, but the readback is this one is always reading the full buffer because it doesn't know about the counter. So yes, so to read only the relevant part, it's of course possible. So the first thing is the counter is stored in the it's not stored in the buffer. The counter is stored in the view, so it's stored somewhere on the graphics card. Normally it's some form of cached version. So that means we first need to get this, how many elements are in that counter at the end of processing. So the first thing you need to do is then copy counter, which will take, it will take the counter of which is in the view, and it will copy it into a buffer. So the counter will be the first element of a small, it's a small buffer, and it will be the first element. Then you can read back buffer row, and you want to read int, and you want 16. Ah, and it's not resetting for some reason. I should not even.
It is just an integer, right?
It is, yeah.
16.
Because actually buffer, some buffer have limitations, so I always create them of size 16. Because, like for example, constant buffer, they have to be set as a multiple of 16. You're not allowed to do a constant buffer of size 15. It has to be a multiple. So generally, all my buffers, I tend to do them as a multiple of 16. It's just me. That's not. It's just that it's consistent with the rest of the pipeline. It's just for that reason. But yeah, normally I could totally have a buffer which has a size of 4. That will totally be allowed. Yes.
Isn't it unit?
Hmm?
Copy counter. Isn't it unsigned integer for the copy counter?
Sorry?
Isn't it unsigned unit?
Yeah, but that normally should be casted. So.
Yeah.
Okay, well, it's giving me some. Yeah, I don't know why this one is not here, but yeah, readback should return 0 or 1 in that scenario. But I got a small bug by the look of it. I think it's something I need to. It's something which will go in the Git issue for some reason, but it should really work. It's a bit worrying that this one is not.
Before you were totally fine, but
Yeah, that's strange.
by the way,
Yeah, and then in that case, well, if I just finish, in that case you have this. Yeah, in that case you have this readback called region. So that means when you do a readback, what you do, the process is you create a buffer which is called staging, which is accessible by the CPU to read, and you take this GPU buffer is copied to this CPU accessible buffer. It's using copy resource, and then from there you can say I need to map this buffer. I need to give me read access to this buffer. So that's what's a readback process. But the idea is you can also say copy only a part of the buffer. So that's what readback region does. So instead of saying copy me 512 elements, you can say copy me 2 elements, for example. So if I go back to this one and I set it as int, so this one will read, say, I want to read only 1 element. So instead of doing a full copy of everything. This one will say, just copy, you can really say copy this mini block of memory to this other mini block of memory. So it's read-back region was done for that very purpose, actually.
So
to say.
you're saying this is more optimized, basically. If we were to get a copy counter, especially, to use read-back region element?
Well, if you need to do selection, if you start to have 1 million elements, you will need to download 1 million elements back, which is obviously not so efficient here. It even does it at the copy level, so that means it will only copy n elements on the staging buffer. So it will don't even copy the whole resource in staging and give you read access to a small part of it. It will copy only a small part. So yes, you should, if you need to select to use filtered element, region will be more efficient because it's less copy, it's less size. So yes, it is.
And sorry, that kind of goes to my point. I was making the mistake at some point of reading back the copy counter on Append Buffer to get the element number to somehow optimize. I realize it's fucking stupid now, but can you confirm that basically with an Append Buffer you have to have the element count in your render as whatever as high it could be?
Yes, like append, well, if you want to consider append buffer, actually append buffer is really, let's call it stupid. It's the same, it does nothing for you. So append buffer is just a counter, and when you call append, it says add 1 to this counter and write in that counter in the previous counter value. That's all append does. But if you set your counter to 5 million, then your reset value to 5 million, it will go to 5 million. So, and if you go over the buffer capacity, you will also go over the buffer capacity. So that means it's not trying to do anything for you. So if you append too much, you will start to write out of bounds as well. But the idea of append is you need to find a buffer size which is big enough for what you need. And then you use append because after you can use those indirect dispatch or indirect draw, which allow you to only process this part of the buffer.
Yeah, according to the dynamic copy counter, you're saying
yes.
that we can grab that back and keep it in the pipeline.
Yes.
Further down the line, we're using indirect and then we use the dynamic element.
Yeah, when you use indirect, it will use copy counter, but it will do a GPU version. Like
yes.
Copy counter does a GPU version,
yes.
but
copy counter is only really for debugging, right?
Debugging or saving something. If you need to save your data, you need to read back and you need to know how many elements. One thing which is important with append though is now you have no order guarantee. Yes, exactly.
Jesus Christ.
If I do a 256 by 256 element, that's maybe a bit too much. 64 will do.
Do that? Is it more optimized? I don't understand how you've got an array. Let's say, sorry, I know it's a buffer, but you've got an array of elements, and then suddenly, if I remove the indices and just brutally force things in a random order, that's more optimized?
Yes. Yeah, because you don't have to care about order. The less you care about order, you just have to, you do one interlock operation versus you have to make sure everything is in the same order from last frame. So you need to keep track of what was there last frame to make sure this is in the same order. It's actually really would be quite impossible actually to do. So you have to make sure you lose all the parallel aspect basically. That's why in GS it's guaranteed that it will happen, but GS is very serial, so it's not too, that's why GS is much slower, but then you have this order guarantee. In compute, you will have the same result, but in a different order. So you have to take that into account. If you use append and you have read back, you might have this big flickering data because it's always the same values, but in different order. But in the case you don't have any order, if you don't need the order requirement, append is perfectly fitting.
Could you maybe go into, if you like, how to regain the order, like having two buffers, or just the basic concept
Well, you have to do prefix sum basically. So you know this integral node. So which does like integral is exactly, it's a prefix sum basically. So you have to say no, like you have to do this Boolean version. So is it hit or not? And from this hit or not, you build a table. So if I do it for 4 elements, actually I say this one is a hit, this one is a hit. And that will give you the right index, you see? Because now suddenly this doesn't need to be written, this will need to be written at index 0, this will be needed to be written at index 2. So you need to perform that integral node in GPU, which is actually not super straightforward. But you need to build this index table, which will give you a guaranteed order, and then you use a writing index which is from here, which will give you the right order where to process the element. Actually, I do probably... I have a 2D version I can show you. Actually, I don't have a 1D version of this, but I have a 2D version, so... I should be around here. No? Ah, no, that's for direct. No. Forgot which one is it. Ah, I should have one of those special ones. Come on. No. It's not here, come on. Sorry? Yes, I'm just trying to find where... Ah, spatial grids, there we go. Yeah, that's actually, that one is a 2D version, so it's the same concept but in 2D, but that will do some, it's an integral in 2D, this one. I don't have a 1D version by hand. I think if you look in NVIDIA samples, they should have one, it's called prefix sum. Well, they have a dynamic tessellation in compute also. They have a compute version of adaptive tessellation, so they definitely use prefix sum, but that's a 1D. That's a 1D version. Basically, I do it. You divide it like so. You do MIP level. That's the idea. So you do a add as MIP level. So basically, at the end, you have the sum of the count in one place, and then you expand back. It's quite tricky to explain without drawing. Let's do it with our favorite tool. Yeah, I need a workshop on Paint, please, for next year. So the idea, well, these algorithms are really serial, so they are not straightforward to do in GPU. So what you will do is you need to do this divide version. So what you will do, you need to sum the element from the neighbor, but because addition is like if you do A plus B plus C, it's the same as A plus B on the result of A plus B plus C. So the order doesn't matter. So because order doesn't matter, you can do this form of divide. So what you will do is if you're in 1D, you will do one version like here. So you do one pass, which, say for example, do the sum of a 4 by 1 block. So you have a 4 by 1 block, which you do the sum 0, 1, 2, 3 in a smaller buffer. Then you have one place in the pixel shader which does the sum of those 4 elements. So you do a 4 by 4 part, and then in the next iteration, you can do the sum of this result here and this result here. So you just divide blocks like this.
Sorry, so just to conclude on this whole thing, when you would have to do this, because that sounds kind of insane.
That's a pain to do, yes.
But
It's quite
so I'm
annoying.
saying, are we saying that like the solution could be to not use an append buffer and just do a check and maybe create transformation matrix that hide the element if they are like instance cube or something like that, or is it I don't know, is there another solution?
Well, it's not so common that I really need order. So the fact of needing order is not necessarily common, because when you think of rendering in 3D, at some point it will have to go through depth buffer. So that means the processing doesn't need to necessarily be in order. You have many scenarios you don't care, basically. Like there's much more scenario where you will not need it. You think you need it, but when you think about it at the end, you don't really need it. The only case you will need to preserve order is if you need alpha. So obviously you still need to process element in the same order, otherwise you will have flickering because you're doing alpha blending and you don't have depth buffer. But for anything which is standard solid geometry, because depth buffer takes care of that later, the order is never really important. If you want to do it another way, you can also select and sort the selection. If you want to process in order, you can also do a sort. That's one other option, but that's also not funny. I'd say the integral version is probably an easier version than the sort version. But yeah, the idea is now you have one buffer with that element, so you can also do things like you can do things which only process this element. So the fact of using append buffer is also important for optimization, because now if you want to say if you want to think about it of these elements as a lot of particles, and you want to say this element that got hit, I want to put a really heavy attractor to it, for example, like just I want to apply big attractor complicated force field just to this element. Yeah, just to this element that got hit, or for example you want to say no, this element that got hit, I want to display it as a, I don't know, as a quad, for example, but only this element. So you would, if you do it with a constant color here, you would have to say, if it's not hit, put a quad of 0. Whereas here you can just use index indirect, and let's do a quad. Actually, that was perfect. And we connect our index indirect here, and we need to say this is the instance argument buffer. So that's in here, and well, we do a constant instant. I need to clone it still. ID here and group. And so now we're here, and so now if we want to only process the elements that got filtered, what we do is we have the location of what's hit, so it's inside that buffer, and we have the number of elements that got hit in that copy counter. In the actually it can be anything, because here there's also overlapping elements, so that means it can be 0, 1, 2, 3, it can be any number. This number is just stored on the card, so we don't know it. So what we use is we have this indirect version. So like when you do draw instance, you basically at some point say the instance count on the CPU. So you have to say how many indexes your geometry has and how many instances your geometry has. So the indirect version is, instead of setting that in CPU as a number, you have a buffer in GPU which contains the same data. So the idea is by index indirect is you have your renderer here. And this counter gets copied as instance count. So you do a GPU copy in the instance count location, you do a GPU copy of this counter. So it will make sure it only draws this element. And I really have a weird bug in my build, actually. Because it's not making sense at all.
Are you sure the readback should be raw if it's a copy counter?
Yeah, because in copy counter case, I copy to raw buffer, so yes, it is. It's like it was a choice. I mean, it makes no sense. Actually, all the readback should just be, I think I started to add it, but all the readback, soon they will just be readback buffer. Because actually it's just a buffer. Actually the fact of structured or raw, it's just you, when you create this buffer, you specify what you want to do with it. But actually readback can work on any buffer, so technically readback should just be readback buffer, and that's it.
So like when you can't connect the raw buffer to a structured buffer pin, that's just like by design, it's not a...
Yeah, it's by design, because, but normally I should quite allow to connect any buffer to readback buffer. That should be even, but the thing is, yeah, like for example, structured buffer, the size calculation is a bit different, but I should really be able to connect any buffer.
Seems like here you're trying to make an instancing, but I think the constant which you plot is not.
Yeah, I did not grab it, but there's a really small bug in that renderer somehow, so it's very annoying. Yeah. I'll just try. Okay, I'll just try with that one quickly to see if I have the same issue. Just.
Transactions between GPU and CPU are always really expensive.
Yes. Okay, and.
Yeah, readbacks are terrible.
This is old build. What that will do then? No, it does the same. Okay. Ah, okay. Oh, that's actually my build was totally okay. That's me who is silly. Yeah, it totally makes sense. Yeah, because actually that's exactly why you should. That's a good thing. Like I should read. That's exactly why you need to have this element count, but this element count need to be connected to the right value. Yeah, so now it's working. Well, I'll show, actually there's one example here, so I'll do it a bit quicker. Yeah, this one will just show it as an example. It's the same concept, so I'll just show a direct version. So the idea is this one does the same, so you only thing is instead of checking a mouse hit, it just checks if the element is lower. And then you have this index indirect, which copies, oops, like which copies that counter here. And then in the constant, yeah, you have a structured buffer of uint, which is the indices of your element. So when you have your instance ID, you first go look which element it is, which index it is in the filtered list, and from this filtered list you get the real position. So that's how it works with append. You can append the whole position, you can append the whole transform. You don't necessarily need to append the index, but generally it tends to be common that you just append the ID of the element. But if you want to be lazy, you can just say, oh, I can append the whole transform and just use the whole transform directly. You can, you're completely allowed to do that.
Yeah, but it's much more memory.
It's more memory, but it has, sometimes if you need to read it a lot, for example, it will also be in the same layout. So it will be more contiguous. It will be a bit, every element will be closer to each other. So if you really need to read it a lot after, sometimes it's useful. It's always on a case-per-case basis. But the general thing is to start with ID most of the time.
Sorry, I have one question to that. I think I actually kind of meant this example. So now, after the filtering, the elements are not in order anymore. And I think what I tried was after that, like applying a buffer of colors. So they would like flicker around because it's not the right order.
Yep.
But I think what I would have needed to do is just also paint the color. Is that correct?
You can also append the color as extra attributes here.
So that would be
Oh,
a solution for the
yes,
missing-
or if you have the ID, you make sure you use this ID for reading the same color. But yeah, you have different options. But if you need to make sure, yeah, in that case, yeah, you will need to append everything you need. That makes complete sense. So actually, yeah, that's another example. It's a bit simple just before to go to the next one. But yeah, if you use append a lot, you can do also, you can also just debug your counters without going back through GPU. So there's also options to do that. So that's a small, it was working a minute ago before the workshop. Ah, that's the one I deleted. Ah, yes. Ah, and I just deleted it also, that's clever. Ah, well, anyway, I'll just redo it on the fly then, no problem. Layout, well, I'll clone it also, layout text. Well, so the idea is, for example, we have a number in our buffer, so like we have this copy counter, so it's just an int in our buffer. So that's one example of append which can be eventually used. So we actually need append in that case. So what we're gonna do is instead of doing readback, to get this number and see it on the patch and display it with a text node, we actually gonna just take this int and display it directly. We're gonna build the text in compute shader basically. So the first idea is I have the text node here and the texture array renderer. So integer is just only between 0 and 9. It's just a bunch of digits. So basically this one does a texture array, and each slice of the texture array is 0, 1, 2, 3. So if we actually preview here. So it's only this. So every slice of the texture array is just a digit. So now the idea is we have an arbitrary number, so int number equals 1/4, oops, caps lock. So what we want to do is we have this number which is somewhere on the graphics card, and we want to see 164 somewhere here on the screen. So, like we can do that. So we can do that with append. So the first thing is we have, like we need to know how many digits this number is gonna be. So because like to get the number of digits for number, we can use log operator. So log, if we see like 14589, for example, log operator is 4 point something. So actually the next int, you need 5 digits. So you can know how many digits you need from this number. So int digits equals log, I think it's log 10 directly, number. And it's a floor, is it floor or cell? I think it's cell. And yeah, with append you can append obviously never, but you're also allowed to append several times. You're not. It's not like if you want to append 20 elements because of any reason, you can append 20 times if you want. So you're not limited to 0, 1, something. You can append as much data as you want per thread. That should be. And yeah, it got really append complete broken, so I really have to fix that in my DX build because I think there's something really bad in there. Yeah, I guess you will have a new DX11 build quite soon during Node.
Oh, that's right, as always.
Yes. Okay, so well.
Origin and spacing set on your end. Do you have origin and spacing set?
Well, let's recheck quickly maybe. Well, it was pushing 0 as a counter. That doesn't sound too good also. Why? Okay. That's probably why. Because I cloned to the wrong one. Okay, that makes sense. But the read back still makes really 0 sense. No, it should be. Uh, 164. Sorry? Yeah, it should be still here anyway. Well, it should be the next integer, so the problem is you'll have the rounding. But yeah, the idea is you do the modulo version, so that gets you digit index, and then you can append digits. So you do a bit of custom spacing. Okay, what is the time now? Oh, still. Okay, so one thing, yeah, we'll go through next example. It's still back to hit test anyway. But yeah, one of the thing, well, obviously the fact of you have read-write buffer, the fact of read-write buffer means it's read-write. So that means you can also preserve the state. So that means like if you think of some 4v nodes, for example, like toggle, like if you want to do a toggle, like if I get this example of a hit test here, I just say every time I click on the mouse, I need to swap the value. So that means I need to preserve some state of the previous element. So that's obviously because everything is read-write, we're gonna write a toggle version. So now if we, in compute, if we hit this element, we want to swap the value. We don't want to know if it's hit, we just want to swap the value when we hit. And when we right-click, we want to just reset everything to 0. So it's like the same as a toggle node if you want to think a toggle animation. So it's a compute version. So you have, the first thing is the reset. So the reset, you only enable it on mouse right-click in that case. And reset is obviously really straightforward. You just have your output buffer with the state, which is on or off, because it's, and you do output buffer equals 0 to say turn everything off, basically. That's as simple as that. Yeah, here, well, I tend to use integer because Boolean is the exact same size as int. So, but sometimes I interpret Boolean a bit differently, so I tend to prefer int in that case. So just 1 means true and 0 means false. That's it. And now we have our little different version. So we have our int for output buffer, which contains our state. But what we can do is, because it's read-write, that means in the same dispatch you can read this element and you can write again. So you can perform both operations. You're not write only like we did for reverse. We were only writing to a buffer and only reading to another one. In that case, we can really say grab the value in there and change it. So you can just do something like, for example, just a plus equal operator. Like a plus equal operator in compute, you just do plus equal. So you don't have to think about complicated things. You can just take the value and do something with it. So in that case, we still have our favorite safeguard. Now we get the current value. So we check, are you on or are you off? We get this world transform. We get the position from the mouse, and we do our hit test value. And in the case, now what we say is if you hit, just flip the value. So you say current is, if element is hit, just flip it. If it's not hit, just say stay as you are, basically. And we just write back this new state in the buffer. So that means, like across frames, now we have the values which are preserved across frames. So you can do pretty much all the Boolean nodes you have in 4V, this toggle, which all of them which can become quite expensive at some point. That's the same. You can all write them in compute, and they're really easy to write, as you can see. It's not anything, because as soon as you get read write, everything becomes simple because the state is already there, so you just read it. If you want to do like a different version, we can do the flip-flop version, so just to be a bit. So hit test will do flip-flop. Well, flip-flop is actually even easier than like flip-flop in 4V is as if you set once, you just keep it on all the time until you reset. So like if we check the flip-flop back, I guess everyone knows that node, but just so as soon as you set on, it stays on until at some point you reset. So it's just like signal once. So now what you just have to do is so now you just say no if you check if the element is hit, and if the element is hit, you set it to true. So otherwise you just keep the same value. So now if we reset, yeah, and now you can see the compute version does different because that one is CPU toggled. So if we do flip-flop animation here, set, okay, and reset, now they're behaving the same. So now we have the flip-flop version. So it's really easy to add them again. Now we can do more, like what you can do is you also can do any of those timed animation version also. So for example, if you want to do something like monoflop, which will be a bit of which will add a bit of complexity because you suddenly have a time factor. So it means you need to keep it on for a certain amount of time. So let's actually do that one. So we do monoflop version, monoflop animation. So monoflop will keep it to 1 second. So it will just keep it on for, it's like a gate basically, for people who are not too familiar with that node. So now the only thing we need to do is we don't have so we need to change our output structure because now the state we can't really fit the state in int. Well, we actually kinda could, but let's try to do it. So struct state, and we'll get int is on, and we get a float time since on. So now we have one int and one float as our structured, and we want, so our read write becomes let's clone that one too, monoflop please. Well, fine. Okay. So now the only difference is our state is quite our state needs this time, so we need to know how long this element's been on because we need to switch it off at some point automatically. So now we need to read write states obviously. And so state current equals so now we'll do it with a if here. So if we hit, we need to say current dot is on equal true, 1, and current dot, well, I'll just call it time equals 0.0. So that when we hit, we want to reset the timer always. And if it's not hit, we need to check if the time, if it's been on since a certain amount of time, we need to turn it off again. So in case it's not hit, we need a float time. So now we need to calculate the delta. So dt equals time minus current dot time, and we'll keep also float. What's the name of max time in that case equals 1. So we have our delta, so we know since how long it's been. So, and if delta is more than max time, then actually current dot is on equals 0. That's about that. And here actually we'll actually, instead of storing 0, we'll store the current time instead. So we will use a stopwatch as a time input. So we will say at this moment in the stopwatch, this element got hit basically. So we can use it direct. And well, we just don't need this anymore. Output buffer is current. And we use a stopwatch here and as a time. And the only difference is here now. Also, like we need to have our buffer input, we need to read it. It's not a bool int anymore. So sorry?
You save it and
Yeah, they're all cloned and saved, so I'll put them in contrib, of course. That's the idea, to have the initial one, but to have the final version too. And now the thing is, our stride is obviously 8 too. Yes. Yes, only difference is also in the previous case of tug edge, yeah, I was always only running the compute shader when there was a mouse click, because for toggle I only wanted a mouse click. But now, because we have this time factor, we need to run the compute shader all the time. So that means instead here we do need to enable it like this. And that means that means now if we want to use right click, well, you have two versions. You can do everything inside again. So you say bool process equals false. Yeah. So yeah, you have a Boolean to say add it as an extra condition. Or what you can do is you can also create two techniques. So because here you're still processing everything all the time. So you're still trying to perform the hit test all the time. But if there's no mouse click, you should just check the timing instead. So we'll actually do that one too. So the idea is instead we will split the work in two different compute shaders. So we will run one compute shader if the mouse click button is down, and we will run one compute shader if the mouse button is up. So if the mouse button is down, we need to still perform the whole testing. But if the mouse button is up, we only need to do the time check to reset the values. So instead of doing everything in one unit, we can also split the workload in different units. So actually, it's quite straightforward because we only need to remove code, more or less, and move things around. So we have a CS delta, which we'll call, and we will exactly copy that one. And the CS delta is when the mouse is off, so it doesn't really have to check anything. So only thing we have to check is if current dot is on equals 1, and we get rid of pretty much all of it. And we need to change it to CS underscore delta. So the idea is we process everything if the mouse is on in one pass, but if the mouse is off, we can optimize a little further and say, okay, just add the, if for only elements that are on, you add the time and process the reset. So now you have two techniques, apply on delta, and you do odd to enum. Well, I guess that should work in that case. That should redo the enum in that case. What we'll want is we want to keep the same order. So apply will be 1 and delta will be 0 to avoid all this Boolean flipping. So like order is just set in that order. So we just say 0 will means technique 0 is mouse off and technique 1 is mouse on. So it's a bit easier to process. So yeah, now it's, and we have our mouse target order to enum here. And so now we have our monoflop working in compute shader. So yeah, when you start to have all these animation nodes in 4V, they can tend to become quite heavy at some point. If you really have large spread counts, they can become really heavy. So it's really effective, and I mean the amount of time to have a compute version of it, like the time invested into writing it in compute versus reward of having much better performance is pretty decent, let's call it like that. So for any node which can start to become a bit of bottleneck, a lot of those nodes can really quickly become, it's really easy to build a compute version because there's all the read-write, the whole spread one is you write the same operator. And because compute already does the loop for you, like if you do it in dynamic plugin, you still have to take care of the spreading and looping, but actually in compute, because it's already doing that, you don't even have to write this loop code yourself. So yeah, it's pretty good investment, reward versus investment for many use cases. So like all these animation ones, they are pretty good case. What you can also do, for example, here is if you want to animate, you can, now instead of having it as 0 or 1, because we have this time input, Control Shift S again, and we're gonna say fade. So the idea is instead of having this 0, 1, so this pink or yellow, what we want is we want to gradually fade from pink to yellow, for example, with the monoflop. So that's actually you'd have quite nothing to do in that case. So timed underscore lerp. And now you instead, you already have this time, so we'll still say, okay, a time of 1 will be full other color. So we're gonna get our state again. Okay, now we need to get our full state because we need to access this time because we want to fade the color depending on how long it's been hit since. And actually, and we need our time also as input, so float time. And we need to calculate the delta. Sorry?
The II, can you quickly explain what that meant, the input of II?
That's the instance ID.
Oh, okay.
It's like I do, I have a batch buffer, I have a dynamic buffer to read elements. And so now we have our state here. Now we need to get the delta of our state. And if our current element is on, else, so if it's not on, we still use color without hit as before, but now if it's on, we have output color equals output.color equals, so now we're gonna interpolate, so it's like color no hit, color hit, and I'll just use delta, but we could have a speed parameter. Well, we can add any of those really quickly, but for now it will be us, and we of course remove that line. And float time, also float time. And we need to connect, make sure our stopwatch here is also going here. And now we have a animated version, so by also quickly changing vertex shader, we can easily build this type of animation. So the whole process, because everything is instant, so the whole process is really fast, and everything is really streamlined because you have access to this state. So you can also, you can use this value not only as for the behavior, but you can reuse this time value you have on your state as an animation parameter. So if you want, you can do something like this one. So we'll do something like that also. Like we also scale it, for example. So input. Okay. Well. Okay, so this one is not too happy to. Okay, fine, right? Yeah, you can use this time parameter for obviously any animation. So, like here, you can also say, I want to scale the object on, like, let's do 1.0 minus. Yes. So yeah, just also in like the good advantage with compute is you can really, after in vertex shader, it's really easy to add this type of animation. So you could actually process a buffer which contains the scaling and everything in compute also. But together with vertex buffer, it's really easy. You suddenly have the whole state, and in vertex shader, you can all easily do this scale, translation, color, morphing. All these small operators are really easy to do in vertex shader. So combined with vertex shader, you can create some quite really complicated type of behaviors. I don't know if there's any other one in the flop version. Flop. And yeah, of course you can, you can change your hit test function. So if you need to do a square hit instead, it's quite easy. So like you have circle, sphere. If you need 3D, you can perform all those raycast version too. There's tons of different versions to do. So anyone got question also?
How you skin to your detail?
Sorry?
How you skin to your detail?
How what, sorry?
Skinned, like turned to black, the detail.
You don't, sorry.
Or the detail. I mean,
This, you have to go through, yes, it's true. There's this question.
Oh, that's how you color this editor? Yeah, there's an XML file.
You go in this lib, it's third. Yes, I know. Yeah, you have this one here. So you have this XLSL mod, and you have
You open source that.
which
Yeah, put that on GitHub.
dark sim. Yes, true. Actually.
Sell it.
Yes. Yeah, actually, it's.
Take a picture.
Yeah, scroll all the way down so you can yeah, keep going.
Yeah, actually, you go modify here. On this one, I also did it for. Yeah, it should have the DX11 keyword. So yeah, I should put that in contrib somehow.
You gotta go all the way down.
Man, there's a lot of code to type manually, bro.
Yeah, so you have all keywords. You create category. You say if they bold, italic, color, and you just put keyword. And I think there's a version I need to fix. Yeah, there's something with keyword which should also allow to ignore casing, but I forgot what it is. Another question? No, yes?
I have a harder one. So I got really frustrated with compute shaders because I was trying to do acceleration structures. So
Yes.
like things that you need like a pointer for, like making a tree-like structure.
Yes.
And it basically, like every time I try to do a compute shader with a non-trivial use case, it always like turned, I really wish I had like a pointer. Like, so I'm curious if you run into situations like that when you're transitioning CPU code to GPU code, and what your normal like practices are.
Well, yeah, acceleration structures are always a bit tricky. Well, generally, what I tend to use, I use an int instead. So you replace, instead of using pointer to the next, you use indices. So it's like you, instead of having pointer to the child element, you have int, which is index in the buffer, and you use interlocked operation. Actually, I can show one repo. So it should be in spatial grid. Yeah, this one does linked list.
Is this like a uniform grid or something?
Oh, that's horrible. Visual Studio. Okay. Yeah, so like this one, for example, does a linked list. So, well, it's just a linked list. It's a tree with only one child, if we want to think about it that way. It's like a specific case of a tree. But the idea is you get, so instead of using pointer, you have ID of your element, and then that's next element in the list. And so yeah, this one does, well, build like a linked list of elements per cell. So you have a uniform grid, and you build a linked list of elements per cell. So you have point transform, and in that type of scenario, you need to write to 2 buffers. So you need to do multi-buffer of writing. You can write to up to 8 buffer in Windows 7, and if you're on Windows 8 Plus, you go up to 64. So it's not in the compiler. So normally, as soon as you're on Windows 8, you can write to 64 buffer at the same time. So, well, I never ever went to that, nowhere near close to that limitation, let's call it. I say even 8 is really, it's never happened that I write to more than 8 buffer at the same. I never went through that limitation, but they even expanded it, so that's really. But so in that case, you need 2 buffers. So the idea is you need to say, so well, that's building, so you get, I transform a point in grid space, basically, so that's, the transform is transforming into the distance field space, so unit cube starting at 0 and finishing to 1. Then that gives the cell index. So in that case, I don't have volume for writing. So it's like the buffer is a 3D texture, but that is manually indexed by hand. So that's like write to the 3D cell of that element. So you get the ID of your linked list, and what you need to do is you, in the cell index, you need to increment of 1. So first you increment counter, so you have to push a new element, so that's a new ID. So instead of append buffer, you have counter buffer. So counter buffer is the same. When you call increment, with append, the number is incremented automatically and you don't have access to it. With counter, you just say increment the counter of 1. So it's like, it's doing you do interlocked add, you just do add plus 1. Increment counter is exactly that. You just add 1, but it gives you the value. So now you have the location where to write your element. And you need to exchange the value with the previous one. So like actually the offset buffer contains the location of the last element in the list. Of the first element in the list, sorry. So you build a reversed linked list if you want.
And interlock change?
It's like replace, well, it's basically interlocked exchange is exactly this operation. It's actually doing, interlocked exchange is doing exactly that operation, but it's an atomic operation. So that means if you have two threads that needs to write in this place, it will make sure this will be properly serialized. So order will be not dependent, but if you don't use interlock, you might have 2 elements which try to add at the same time. So that means suddenly, like you can have really race conditions. So if you need to make sure, like you need to exchange in that case.
So this is like a.
It's a guaranteed write. So.
It's like a mutex and multi-threaded CPU stuff. Right?
Yeah, it's exactly. You'll have a mini mutex in the interlock. Well, it's gonna be a spin lock in that type of case because you need very fast type of contention. Well, the safe interlocked is only there because it's not working properly on NVIDIA. That was the main that was the main reason why it was here. It's just like it doesn't work on this card, so I had to write a different version. But yeah, seeing infinite loop in compute is kind of strange. Yeah, that's doing interlocked add. So actually, when you call interlock add, it was doing this loop with interlocked exchange, but it's just it's done by hand because NVIDIA was not doing it properly. Like I always had an issue with the return of the previous value. Like the add was working correctly, but the return of the previous value was not correct in some cases.
Still the case today?
I don't know. I did not try it for quite a while. Like increment counter tends to work really reliably, but interlocked add, I had this really one case where it did not work. So I had, and really only on NVIDIA. I think it's still the case because it's really a specific case where it's your problem, they will say basically. But so yeah, interlock exchange really makes sure that you write the last value, because in that case, sometimes you could have the second to last written, so it makes sure to guarantee that it's written properly. That's the reason for. So you can probably build a bit of tree structure like that, but actually the traversing tends to be, well, the traversing can tend to be quite slow also. But I guess you can probably do a tree structure like that. Another questions? Yes? No?
Can you just keep doing workshops for the rest of Node? You just like go through your files.
Well, a bit early on time, so if you have other question or something you want to, for once, a bit early. So if there's something else you want to see in there, I got examples. If there's something I can check examples or.
Simulations.
Huh?
Fluid simulations. Ooh.
Actually, fluid compute is not really different from pixel version, really. It's like what you like for fluid, you can totally do it in pixel. It's the same. It's the same thing, really. So there's no. Only difference is probably fluid. Yes. Yeah, actually, I probably do use pixel for the 2D version. I can check. Yes, actually, the 2D version is exactly pixel shader version, and the compute version, the 3D version will be compute because you can use RW texture. So I want to write to a volume, but well, you can either do a compute which writes to volume, like standard RW texture, so, and you write to the 3D voxel every time, or you can do the instanced quad version. You can do that in pixel even if you write to 3D texture, you can do that in pixel shader too. So you draw, like if you have a 64 by 64 by 64, you can do, you draw 64 full screen quad, and in geometry shader, you will tell which slice you want to go in.
And you can have like multiple read-write textures as target at the same time?
So yes and no. Like read-write is a bit strange because, well, you have this. It's called typed UAV load, and if you're so it depends on which window